Good morning, everybody. Like I said a little bit earlier, we're starting with Exam 3 review. I just took a few questions from the review that I posted on Blackboard. The answer key is already up, so if you have questions, you can look at that first, and then you can send me a message. We're going to start with this first question here, so if you've just logged in, that's all right. Just go along for the ride. If you've had a chance to work on the problem, you can put your answer in the chat. Which one of these is the predicted atomic radius for selenium? And if you're looking at the question and you're like, I'm not sure, you can say not sure or help, just to give me a feel for where we are. Okay. So let's go over it. This is a problem where you're predicting an atomic radius, and we can predict physical properties and chemical properties based on the grouping of the periodic table. So if you look at the periodic table, you will notice all in a row, you have sulfur, selenium, and tellurium. And this is group 6A. Now we should already know the trend for atomic size or atomic radius. As you go up a group, the atomic radius decreases. And since we have the radius for sulfur and tellurium, that means that the radius for selenium has to be somewhere in between those two. The only one that's between those two radii is C. So it's just a little bit of reasoning. For those of you who said help, does that help? Good. Let's move on to the next question. So this is reviewing noble gas electron configurations for neutral atoms and ions. So I'll give you 5 minutes for this one, and then I'll move on to the next slide where I've got a periodic table and I'll write them all out. So I'll give you 5 minutes and then I'll check back in. It's been about 4 minutes. Does anyone need more time? I'm not going to ask you to write your answers in the chat. I'm just going to go over them and then I'll check in with you to see how many people got it right. But does anyone need more time, or are we ready to go over this one? Okay. So I've got all of our atoms and ions listed below, and I'll do each one in a different color. We're writing the noble gas configuration this time. So we're looking at iron. What noble gas are we going to use for our configuration here? Right. We are in period 1, 2, 3, 4. So that means we're going to use the noble gas from the previous period, which is period 3. That's argon. Then we write in everything that's in between argon and iron. That's 4s2. And then 3d 1, 2, 3, 4, 5, 6. Let's do the next one. This one's an ion. So we're looking at phosphorus that's got an extra 3 electrons. What do we put for this one? I lied. I am asking you for your answers, aren't I? And if you need help with this one, you can say help. So we're looking at the phosphide ion. What configuration did we put for that? Okay. Let me choose a different color here. So we're looking at phosphorus, which typically has 15 electrons, but we've added on 3 more. That means that it has 18 electrons. The other noble gas, or the noble gas that has 18 electrons here, is argon. So it's argon. But I can show you how I got there more than just the shortcut. So if we write out the noble gas configuration for just plain old phosphorus, we would use neon, and then it would be 3s2, 3p3. But we're going to gain 3 electrons. Oops. When we gain those 3 electrons, we're going to put them in the 3p because that's the only place that there's room. So that's where the difference is. But this 3s2, 3p6, that's a full octet there. So instead of using neon, we should actually be using the noble gas that's in the same row as phosphorus. So all of that is the same as saying argon. So you're going to want to use the noble gas that is in the same period when you're looking at an anion, okay? So if I asked you sulfur or chlorine, they would all have the same answer. It would be argon. So how do we feel about that one now? Say better, meh, just let me know something. Okay. Let's do the next one. Oh, I don't have all of these on here. I thought I put enough periodic table. So barium, that is in period 6. And it is a positive ion, which means it is going to lose electrons. So it's going to look like the noble gas in the previous period. If it's in period 6, we're looking for the period 5 noble gas. That's xenon. How do we feel about that one? Because the ions are usually the hardest ones. Okay. For this last one, we're looking at arsenic. We're going to look at the noble gas in the row above, and then we're going to fill in everything between argon and arsenic. Oops. So that's what you should have for arsenic. Use the argon noble gas core, and then 4s2, 3d10, 4p3. Any questions here? You can ask them or say nah. Yeah, with the cations and anions, we're only using that for those with the noble gas configuration. It'll still help you with writing you can still write the regular electron configuration. Just know it's going to look like that particular noble gas. So we didn't do the full electron configurations in chapter 5. We only did the noble gas. So that's all I'm going to ask you about for the exam. Okay, let's move on. I want you to classify and write the chemical formula for the following compounds. Now, on the exam review, I didn't have you classify, but I am having you do that here so we can get a little bit of that practice along with writing chemical formulas. So I'll give you 3 minutes and then I'll check back in. How we doing? Are we ready? You can put your classifications in the chat for A, B, and C. Don't worry about putting the chemical formula. That's a little bit much. Yeah, you can use those abbreviations that I normally use, all the ones I introduced in chapter 6. And if you're struggling, let me know. You can say help. I'm going to start slowly filling these in. Zinc carbonate is a ternary ionic compound. It's a metal, plus carbonate is a polyatomic anion. So that's a ternary ionic compound. Tin 4 chloride is a binary ionic compound because it's comprised of a metal and a nonmetal. Dinitrogen pentoxide, there's 2 nonmetals here. So it's going to be a binary molecular compound. For the chemical formulas, zinc has a charge of 2+. It is a transition metal, but it's an exception to the rule. It only has one ionic charge. Carbonate, you would have to look up on that polyatomic ion sheet, and you'll see that CO3 2 minus. So zinc carbonate should look like that. Tin 4 chloride. Tin 4 tells us what the charge is. So tin is SN, and its charge is 4 plus. Chloride, well, we're looking at this first piece here, the chlor, that tells us it's chlorine. Chlorine is in group 7A, which means its charge is equal to 7 minus 8. You take that group number and subtract 8. That gives you -1. So the chloride ion is Cl minus. To write out the actual chemical formula, we're going to need 4 of those chloride ions because tin is 4 plus. And finally for C, we're literally going to write out the first element is nitrogen. The dye tells us we have 2. The second element we get from the ox, that's oxygen. And the pent is for 5. So it should be N2O5. How did we do on that? Did we get them all right? Meh, we got 1 right or none right. How do we feel about the naming and classifying? If you don't feel good, you can say that too. So I'm going to have more of the naming and classifying in the Chapter 7 lecture. So Chapter 7 is on chemical reactions. We're going to be writing chemical equations as in words. We're going to be taking words and writing chemical equations. You're going to learn some different reaction types, and we're going to balance equations. That's kind of the main things. We're also going to look at the evidence for a chemical reaction taking place. I encourage you to watch the video that is on YouTube. This is a very abbreviated version, so you will need more detail than this to complete your homework. I'll try to point out along the way where you're going to definitely want to pay attention to the video and the types of questions you might see on the homework that I didn't explicitly go over between this lecture and the YouTube lecture, but you have the information to do. So I know y'all are probably thinking about exam 3, but try to push that aside a little bit so we can talk about Chapter 7. Are there any questions about logistics for exam 3 before I move on to Chapter 7 stuff? It's going to be set up the same way. Exam 3 folder shows up on Wednesday. You have until 11:59 on Friday to start the exam. Again, you do not need to upload your work because this is really just concepts. So it's naming and periodic trends and things like that. So it's going to be multiple choice, matching, that kind of thing. Are there any questions about the logistics for the exam? I'm going to take your silence as a no, but you know I like my feedback. You can just tell me no, we're good. So chapter 7. The first thing we're going to start with is evidence for chemical reactions. So there's 4 different types of evidence or observations that you can observe that will indicate a chemical reaction is taking place. You do not need to observe all 4. You just need one. The first one we'll talk about is a gas being produced. So you add one thing to another and you start to see some bubbles. That's a gas being produced. In the image here, you're adding magnesium metal to an acid and you're seeing some bubbling happening at the top. That's the release of hydrogen gas. So that's one type of evidence. The second type is you produce some kind of insoluble solid. So you're mixing 2 solutions and then all of a sudden you have something appear. That insoluble solid is called a precipitate. And that is evidence that a chemical reaction has occurred. You used to have 2 things in solution, you mix those 2 things together, and something falls out of solution. We good so far? All right. The third piece of evidence you might see is a permanent color change. Lots of the transition metals have pretty colors. So for example, copper 2 sulfate is a very pretty blue color. You might see green, you might see manganese can have this kind of pinkish magenta color, depending on what compound it's in. So color change indicates that you've made a new substance. And the last piece of evidence that you might observe is an energy change. So you put 2 things together and the beaker gets hot or it gets cold. We're talking about an exothermic or endothermic reaction, and you will need to know those terms. So an exothermic reaction is one where heat is released. If you mix an acid and a base, the flask or the beaker is going to get warm. You can feel that with your hands. That is an exothermic reaction. Some reactions require heat, and so they absorb that heat from the surroundings. In those reactions, the flask will get cold. That's an endothermic reaction. So you will need to know those 2 terms. Let's just do a quick little practice. Chemical reaction or no? The first one, you're mixing baking soda and vinegar and you form some bubbles. Chemical reaction or no? You can put CR for chemical reaction, or you can put no. So number 1, chemical reaction or no? Yeah, this one's a chemical reaction. And if you've ever done a baking soda volcano, you've done this before. Baking soda, vinegar, you usually dissolve the baking soda in a little bit of water, and you have a little dish detergent so that when the bubbles form, it's a little bit more dramatic. Add some food coloring. So that's all number 1 is. It's a baking soda volcano. Number 2, cooling carbon dioxide results in the formation of dry ice. Chemical reaction or no? It is not a chemical reaction. So I know it may seem a little confusing because you're cooling something, but that's not the same. This is a state of matter change. So this is a physical change. Carbon dioxide gas, you can cool it down to form dry ice. That's not changing the chemical composition of carbon dioxide. It's just changing the state of matter from a gas to a solid. And number 3, 2 liquids are combined and a green precipitate forms. Chemical reaction or no? It's a chemical reaction. You mix 2 things, you form a solid, and it's a different color. So you're seeing a couple of different pieces of evidence, a color change and something solid is forming. So you will need to be able to identify chemical reactions versus not. I also reviewed chemical and physical changes in the YouTube video. So that should be a review from chapter 3. So make sure that you are up on that with chemical and physical changes. Now we're going to move on to build up a little information so we can write a chemical equation in words. The first thing I'm going to give you is this table that has symbols you're going to encounter in a chemical equation. You're going to see an arrow, so that's here. And that just means produces or yields or gives. It's what separates the reactants from the products. The reactants are like the ingredients. So if you were going to bake a cake, you would gather the flour and the sugar and butter and all that stuff. Those are the ingredients. Your products are exactly that. It's what you make. So the cake would be the finished product. In a chemical reaction, you've got new compounds that are formed. You may have multiple reactants or multiple products. To separate those, there's a plus sign in between. I'm just going right down the list. Some reactions require heat. So those endothermic reactions, they require heat. The way that you signify that is you put a triangle or a delta sign over the yield sign. So that's supposed to kind of symbolize like the Bunsen burner flame. That indicates you need heat. You might also need some kind of a catalyst. A catalyst is something that's not consumed during the reaction. So it may be iron or platinum. It's just something that helps speed it along, but it's not actually consumed. And if I'm going a little too fast and you need to catch up, let me know. But I would encourage you to print out this table or write it in your notebook so that you have it as a reference. Most of these are fairly intuitive, though. NR is for no reaction. So if you mix 2 solutions, let's say, and nothing happens, you don't see a color change, no fizzing, no nothing. It's no reaction. These last 4 relate to the state of matter of whatever compound in the equation. So you have to indicate whether it's solid, liquid, gas, or aqueous solution, which means dissolved in water. Does anyone need more time to put this in their notes, or are we ready to move on? Okay. The second bit of information I'm going to give you before we start writing our chemical equations in words is diatomic molecules. So there are some elements that exist in nature as two atom molecules called diatomic molecules. Di means two, so two atoms. You're going to need to know these, and I have another slide. So in the YouTube lecture, I have a slide that has these listed in addition to this slide. But helium, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they are all diatomic molecules in nature. So when you're writing them in a reaction, you're always going to write N2, not just N. Okay, just writing N would be wrong. One of the ways to remember these, so in addition to the hydrogen, the others form a 7 on the periodic table. We're pretty much looking at the large majority of the non-metals that do chemistry. So you'll need to take note of these diatomic molecules. With that, we're going to go ahead and write a chemical equation in words. So I'm going to show you how I do it, and then I'll give you an opportunity to do some practice. We're going to label this a little bit. We've got the reactants on the left side of the arrow. We've only got one product, so, product side. I start by listing everything and naming it. Whenever you see a metal followed by an S sign, that just means that you have, in this case, solid cobalt or solid magnesium, something like that. So I would call that solid cobalt metal. O2 is one of our diatomic molecules. So that's oxygen gas. This third compound, you should be able to name. So I want you to classify and name this third compound. I'll give you a minute to think about it. I told you I was going to give you more practice for this. So how would we classify this compound, CO2O3? It's a binary ionic compound. It's a metal plus a nonmetal. Now, cobalt is a transition metal, so we don't know its charge right away. But we can figure out the charge on the oxide ion. Oxide comes from oxygen, which is a group 6A element. To figure out the charge, you take the group number 6, subtract 8, that gives you -2. So each oxide ion has a -2 charge. There are 3 of them, so that means we've got a total negative charge of -6. We've got 2 cobalt atoms, or ions, and that 2 times something has to give us a +6 for us to have a neutral compound. So the charge for cobalt must be 3 plus. Now that we know the charge on the cobalt, we can write the name. We had to use the stock system here again because cobalt is a transition metal. So if that seemed completely foreign to you, please go back and review chapter 6. So we've named all of our compounds. Now we've got to write about them. So I'm going to do this in different colors. I'm going to write about the reactants in that blue. So the first part is just describing what the reactants are. We've got solid cobalt metal and oxygen gas. Notice how I'm indicating the state of matter along with the name of the compound. Now we've got to handle this yield sign with the triangle. You can use a phrase like are heated to yield. And that's perfectly fine. Now we have to describe our product. And we already named it, so that makes life easier. Solid cobalt 3 oxide. So does everybody see the pieces of writing a chemical equation in words? We've got our reactants, then the yield sign, and if there's any kind of a heat or catalyst, and then the products. How do we feel about that? Your answer does not always have to be good. Don't feel like you have to only answer if it's good. Class is for everybody. So if you're like, that don't work, that's fine too. Let me know. So let's do some more practice. Here's another equation. What I want you to do first is go through and name all of these compounds. This is good practice for your exam. So name all of these compounds, and then I'll give you 3 minutes to name all of these compounds. And then if you finish that up, you can start trying to write this in words in your notebook, or at least be thinking about it, what you would write if you were writing this equation in words. So 3 minutes. This is completely off topic, but did anybody else wake up this morning and be kind of surprised and angry at how cool it was? Like, it feels like summer just decided to leave. It didn't give 2 weeks notice. It just left the job. And all of a sudden my house is cold. And I'm not happy about that. Am I the only one? Because this just feels unreasonable and unfair. I lived in the cold for 6 years, lived in Michigan. I'm off that noise. Y'all can have that cold. My husband loves cooler weather. And I'm just like, look, we're not polar bears. I don't need it to be this frigid in my home. Well, at least somebody's happy. I'm not. I was like, I need socks? What is this? I'm in my own home. It's 6 a.m. Why do I need to put on socks? Anyway, I just feel some type of way. Just feel some type of way. Not at all related to chemistry, but I just needed to know if I was by myself. So let's start naming these compounds. So we've got a mixture of binary ionic and ternary ionic compounds. For the first one, we need to figure out what the charge is on the lead, because lead can have multiple ionic charges. Using your common ions chart, you should be able to look up nitrate and see that it has a -1 charge. Since there's 2 of them, we've got a total negative charge of -2. That means our lead has to be +2. Now that we know the charge on the lead, we can write out, using the stock system, the name of the compound. The second one, we don't have to do any work like that. We just name the first one. It's lithium. It's a lithium ion, so we get rid of the word ion. And then for the Cl, that's from chlorine. We're going to keep the chlor and add IDE, lithium chloride. Let's make sure that we know what the charge is on the lead. Make sure that we don't have a change in the ionic charge. So we've got Cl2. Cl is in group 7A. Its charge is going to be 7 minus 8, which is -1. And we've got 2 of them. So our total negative charge is -2. For this to be a neutral compound, lead has to have a +2 charge. So we've still got lead 2 with the 2 as a Roman numeral, followed by chloride. And then finally, lithium nitrate. I already know that lithium is +1. It's in group 1. And the nitrate ion is -1. So those are all the names. How did we do with naming? Good. Trying to get in as much practice for y'all as possible. His naming is just one of those things you have to keep practicing over and over and over again until you can practically do it in your sleep. I'm going to keep with the same color scheme when writing out this reaction. I need to make sure that I note the state of matter along with the compound. So I'm just going to say aqueous solutions of, and then write my two compounds. Lead 2 nitrate and lithium chloride. Now we've got to do this yield sign. You can say are combined or are mixed to yield. And that would take care of that. Then you have to list your products. We've got solid lead 2 chloride, and aqueous lithium nitrate. In an exam setting, I'm not going to have you write out everything like this. You'll just need to choose the right one, as a multiple choice or maybe matching or something like that. So you're going to need to be able to recognize all the parts and make sure that you can match the right equation to the right description. So how do we feel about writing chemical equations in words now, after doing another example? So this is one of those things you just have to practice. And if you don't understand the naming from chapter 6, then you're not going to be able to write a chemical equation in words. Now let's go in the opposite direction. There's a written description, and we have to write a chemical equation. I'm going to use the same color scheme to highlight each portion of the reaction. We've got aqueous solutions of lithium iodide and silver nitrate. The first part is always going to be your reactants. Our mix to give, that's our yield sign. And it'll let you know if there's heat or a catalyst or what have you. Silver iodide precipitate and aqueous lithium nitrate. These are our products. So you'll need to take the words or the names of compounds and write them as chemical formulas. So let's do it. We've got lithium iodide and silver nitrate. Lithium iodide, we're starting with the lithium ion, and then iodide, that comes from iodine, and that's just the letter I. So we already know iodine is group 7A. Its charge is going to be -1 as an ion. Lithium is from group 1, and its charge is going to be +1. And we're told that it's an aqueous solution. You don't want to forget the state of matter because you'll lose points. Then we've got silver nitrate. Silver nitrate, we've got silver, which is a transition metal, but it's an exception. It's only got one charge, and that's Ag+. Nitrate, we know is NO3- from our chart. So we can go ahead and write that too. Then we've got our yield sign, and we don't have anything special going on. They're just mixed together. So there's no triangle, there's no catalyst. Now we've got to write our products. We've got silver iodide, precipitate. That means an insoluble solid. So when you see that something is a precipitate, you write it as a solid. And we've got aqueous lithium nitrate. So that's taking the written description and writing a chemical equation. Does everyone follow how I did that piece by piece? Oops. I didn't mean to keep that one in. That's the same thing. Okay. So I'm not going to give you a bunch of practice on the writing things in words. It's kind of hard to do in an online class format. But you will definitely need to be able to do both. Write the equation from the words, write the words from the equation. I'm going to post some Chapter 7 practice problems. There's no chapter check-in for Chapter 7. I just want you to do the Mastering Chemistry, and you have an exam this week. So I'm not trying to add on to that. The Mastering Chemistry is going to be plenty. So we're going to go through classifying chemical reactions. I'm going to fill out this kind of a cheat sheet for you, and then we'll take a break. So we're going to cover 5 types of chemical reactions. The first type is going to be combination reactions, and I'm going to go through each of these, but I just want to give you like the quick and dirty definition, kind of how to recognize these types of reactions first. Then I'll give you a little bit more detail. So a combination reaction, you're taking multiple reactants and making one product. And that product is more complex. So you're taking simple things and making one more complex product. A decomposition reaction is the same thing in reverse. You're taking that one product and it's going to decompose. And both of these usually have heat. It's not a requirement, but heat is usually involved. You're going to take that one product and break it down into multiple products. Oh, should say one reactant. Sorry, y'all. So you can think of combination and decomposition reactions as opposites. Single replacement reactions, we're talking about metals. And here what we're saying is a more active metal replaces a less active metal in solution. There's an activity series that I'm going to go over that lists various metals in order of most active to least active. If you combine a solid metal with an aqueous solution of a ternary ionic compound or a binary ionic compound, if that metal, the solid metal, is more active, it's going to replace what's there. And that'll become more apparent once I show you some examples. Right now, I just want you to have this cheat sheet so that you can remember what each of these reactions are. In a double replacement reaction, you're going to take two ionic compounds in solution and mix them together. They're going to switch anions and form a precipitate. They have to form a precipitate in order for it to be a double replacement reaction. And the final type we're going to cover is neutralization reactions. With these, you're adding an acid and a base together, and you're creating a ternary ionic compound or a binary ionic compound. You'll also see this referred to as a salt. And you're going to make some water. So this is your cheat sheet for the chemical reactions so that you can quickly identify them. Make sure you copy this down in your notes. And when we come back from break, we're going to go over each of these in a little bit more detail. So let's take about 5 minutes. That means at 9:16, 9:7, let's say 9:17, we'll be back. All right, see y'all in about 5 minutes. All right, y'all, it's 9:17. We're going to get back to it. The first reaction that we went over was a combination reaction. And as I said, you're taking simpler substances, you're combining them to make one more complex compound. So I've got some examples of combination reactions where you can take a metal and oxygen gas and you make a metal oxide, non-metal plus oxygen gas, non-metal oxide, and take a metal plus a non-metal and make an ionic compound. So these are just 3 examples of what you might see. I have more concrete examples in the YouTube video. And as part of your homework, you may need to kind of do one of those complete the, so like, what product would you make? So I give you examples that can kind of give you a clue as to how to complete those reactions. So make sure you check out the YouTube video. So that's combination reactions. And decomposition reactions are just the opposite. You take one complex compound and break it down into 2 or more simpler substances. Oftentimes you need heat. Not always required, but most oftentimes you do. So the example I have here is if you heat mercury to oxide, you make mercury metal and oxygen gas. Again, you may see something where you need to complete the reaction. And I've got examples in the YouTube lecture that will help you do that. So you just need to catch on to the pattern for how these things decompose. And I've got more examples too. Let me know if you're still with me, because I know we're just coming off a break. Some people might still be breaking. But just let me know if you're here, alive and well. Appreciate you. Thank you. I know these 2.5-hour classes are rough. It ain't easy on the other side either. So thank you. So we covered combination reactions, which are also sometimes called synthesis reactions. And we covered decomposition reactions. Before we can move on to single replacement reactions, we've got to talk about the activity series. So the activity series just orders the metals relative to their activity. Activity means, can this metal replace another metal in a reaction? I go into more detail in the YouTube video. This relative activity series you will get for your exam 4 and the final exam. So you don't need to memorize it, you just need to know how to use it. Lithium is the most active metal. Everything that comes after it, lithium will replace it. Gold is the least active. It will be replaced by everything that you see here. All the other metals that come before it. Notice that you also see hydrogen, which isn't exactly a metal. This is because some metals can replace hydrogen in acids and water. So this gives you an idea of which metals can definitely replace hydrogen in acids. Water is a little bit different. And I talk about the aqueous acid replacements, which are a type of single replacement, and active metals more specifically in the YouTube video. But we don't have time to go through all of that here today. But I do want to take a minute for you to practice using the activity series. So I've got 3 pairs of metals here. I want you to choose the more active metal in each pair. Again, if a metal comes before another metal, whichever one comes first, that's the one that's more active. So between iron and copper, which one is more active? And we'll do this one in red. So we've got iron here, copper here. Iron comes before the copper, so that means iron is going to be more active. What about the second pair? Strontium and potassium. Potassium comes first, so it's going to be potassium that is more active. What about the final pair? We've got lead and nickel. Nickel comes first, so it's going to be nickel. That's exactly how you're going to use the activity series when we're doing some of these single replacement problems. So a single replacement reaction, you have a more active metal displacing a less active metal in a compound. The example here is we've got some copper 2 sulfate in a beaker. So that's that pretty blue color that I mentioned before. Aqueous solution, so it's dissolved in water. And then you take an iron rod and put it into the solution. Over time, what you're going to see is flakes of metal forming. That's copper solid, because iron is more active than copper. So it replaces the copper in solution. So instead of having copper 2 sulfate, we've now got iron 2 sulfate and then copper metal. So let's do some practice with that idea. I've got the activity series down here below. Let's do the first one. Will cadmium replace iron in the following reaction? We've got cadmium solid, and then we've got iron 2 nitrate. Will we have a reaction? Is there going to be a replacement? There's iron. There's cadmium. Iron is the one that's already in solution. So cadmium, in order for it to replace iron, would have to be somewhere upstream of iron. It's not. So there's no reaction. Does everybody understand that one? What about the second one? Will zinc replace lead, where you have zinc solid and lead 2 nitrate? Lead is pretty close to the end of the line when it comes to activity. Zinc comes before lead. So zinc will replace lead. If zinc replaces lead, we need to be able to write what our products are. So we're going to take the zinc and pair it up with the nitrate. And then this lead becomes just solid metal because it falls out of solution. Does everybody follow that? Because you're going to need to be able to do this kind of thing. Not just say, yes, it will replace, but know what the products are. Like I said, I'm going to post some Chapter 7 practice problems, and you'll be able to do some of these. Now we'll talk about double replacement. So double replacement, we've got 2 ionic compounds in aqueous solution. You mix them together and the anions switch, and you make some kind of an insoluble substance. Remember that that's called the precipitate. So I've got this color coded so you can see how the ion switching takes place. You've got these two solutions. We've got barium chloride and potassium chromate. You mix them together. Now you have barium chromate, which is a solid, and potassium chloride. So they've switched anions and you formed a precipitate. Cannot stress enough that you have to produce a precipitate in order for a reaction to be a double replacement reaction. But the question becomes, how do you know whether or not you're making a precipitate? If you're particularly astute, you may ask that question. And the answer is you have to use the solubility rules. You will receive these rules for exam 4 and the final. They're the rules for solubility of ionic compounds in water. The first half deals with ionic compounds that are typically soluble. And it notes some exceptions. The second half of the rules tell you things that are typically insoluble. So this is kind of like a logic thing. In general, you can summarize the solubility rules by saying anything that's an alkali metal or the ammonium ion, anything that has that, it's going to be soluble. So if it's a compound with lithium, sodium, potassium, or NH4+, if any of those ions are present, it's very likely going to be soluble. Anything that's outside of that, you're going to suspect it to be insoluble. But let's practice using these rules. The first thing I want you to do is write the chemical formulas for these two compounds, tin-2 chromate and lead-2 acetate. If you don't have that common ion sheet, then it's going to be a struggle bus for you. If you do have it, or if you can just quickly go on to Blackboard and look it up in chapter 6, grab it and try to write these chemical formulas. Then we'll reason through together whether or not these are soluble or insoluble. So I'll give you about a minute to get your stuff together. All right, let's write out these formulas. So tin-2, that looks like that, tin-2 plus. Chromate you have to look up. It's also here in rule number 7. And since they have equal but opposite charges, we can just throw it together like that. That's tin-2 chromate. Lead-2 acetate. We've got lead-2 plus. The acetate ion is C2H3O2 1-. We're going to have 2 of those so that we balance out that lead. We've got our chemical formulas. Now let's go through some rules. I'll do the first one with you, and then I want you to tell me what the second one is. So we've got tin-2 chromate. We're dealing with chromates, so you want to find the rule on the periodic table, on the solubility rules that mentions chromates. In general, chromates are insoluble in water, with the exception being the alkali metals and ammonium. We've got tin. tin 2 chromate. So that's going to be insoluble. Does everybody follow that? I found the rule for chromate. Generally, they're insoluble, and the exceptions are the group 1 metals and ammonium. Since I don't have a group 1 metal or ammonium, I'm going to guess that it's insoluble. What about the second one? Lead 2 acetate. Do you think that's going to be soluble or insoluble? If you're struggling, you can say help. That's always an option. If you don't know the answer, you can say help. That at least lets me know you're still with me. The first thing you got to do is find the rule that talks about acetate. That's rule number 2. And we said that the first 5 rules talk about ionic compounds that are generally soluble. So for the acetate ion, things made with the acetate ion are generally soluble. So we're going to say that lead 2 acetate is soluble. Does that make more sense? So I'll give you more practice in the practice problems, but you will want to get familiar with using these solubility rules. You don't need to memorize them. You just need to know how to use them. The final reaction type is neutralization reactions. This is where you're mixing an acid and a base. You're creating water and a salt. A salt being an ionic compound. So I put an example here. We've got sulfuric acid. And remember that an acid is always going to start with hydrogen. We've got a base here as well. Bases have hydroxide. So that's how you can identify acid and a base. And for your products, the potassium sulfate, that is a salt, which is just another word for like an ionic compound. And you always form water. So that's a neutralization reaction. That's the final reaction type. The last part that we're going to focus on is balancing chemical equations. And if we have time at the end, then we can go back to any questions you might have for exam 3. So balancing chemical equations, we're going to be using our chapter 6 knowledge on how to name and write chemical formulas. And then we're also going to need to be able to just simply guess and check to balance the equation. So I'm going to walk you through this problem. You're not always going to get a chemical equation outright. It may be written in words like it is here. So you may have to write your equation out first and then balance it. Here we've got manganese metal with aqueous nickel 2 nitrate. So that's going to be our reactants. And they produce aqueous manganese 2 nitrate and nickel metal. Before we start balancing, does anyone have a guess as to the type of reaction this is? It's a single replacement. The manganese is replacing the nickel in solution. Now that we've got our chemical equation, the first thing you do is take a tally of how many atoms of each element you have on both sides. I use an R for reactants and P for products, and I make a chart. And I list every atom that's in the chemical equation. So we've got manganese, nickel. I'm going to list the nitrate ion as its own thing. Don't need to break up the nitrogen and the oxygen because we see nitrate on both sides. Now we have to count. I've got one manganese atom on one side. I've got one nickel. And I've got 2 nitrates. On the product side, I've got 1, got 2 nitrates, and I've got 1. Well, it looks like this one's already balanced. So that's why you always want to check. Sometimes it may be a trick question. But you wouldn't know that if you didn't make your chart. Does everyone understand how I made that chart? By counting up the different atoms on both sides. This is a part where I tend to lose people for balancing chemical equations, but I will not know that you're lost if you don't say something. Everyone that you get is not going to be balanced. But I wanted to use this example to show you how to make your chart. Let's try balancing one for real. So we've only got 2 atoms here, hydrogen and nitrogen. We've got 2 of each on the reactant side, but then we've got 3 hydrogens on the product side and only 1 nitrogen. So this is very clearly unbalanced. The goal of balancing a chemical equation is to have the same number of atoms on both sides. In this situation, we want to try to balance the most complex compound. We're going to start here with trying to balance out the ammonia. We've got 2 hydrogens on one side and 3 on the other. We need to find the lowest common denominator between 2 and 3. That means you're going to find the smallest number that you can use and divide both 2 and 3 by. Our lowest common denominator is 6. So you can divide 6 by 2, and you can divide 6 by 3. When we do that, we have to alter what's called the coefficients. That's the number that's in front of each of these. If I want to have 6, I'm going to have to multiply by 2 here. And if I want 6 hydrogen atoms on the product or on the reactant side, I need to multiply by 3. So now I'm going to do a new table because I want to look and see what I've done so far. I've multiplied 3 times 2 to give me 6 hydrogen atoms. Haven't done anything to the nitrogen on the reactant side, so it's still 2. On the product side, I've added a coefficient of 2 in front of the ammonia. So that means I'm going to have 2 ammonias times the number of hydrogen atoms that are in them, 3. That gives me a total of 6. And I'm going to do the same thing with the nitrogens. And I'm going to see that I have 2. So it looks like we're balanced. The balanced equation, I'm just writing it out for clarity. Would be like that. So that's our fully balanced equation. How do we feel about that? Okay. So I'm going to give you one to try on your own. You need to take this, write it as a chemical equation from the words, and then balance the equation. I'll give you 5 minutes to do that, and then I'll check in. By show of hands, or by saying me, how many of us are stuck? It's okay to be honest. We're just learning. So if you're stuck, let me know. How many of you were able to get to some kind of an answer? All right. You know I like my feedback. I can't tell where we are if I don't have enough people letting me know how they're doing. I know it's early, but try to bear with me. First thing we have to do is write this equation from the description. I'm going to use the same color scheme. So we can identify our reactants and our products and all that good stuff. It just says iron. So that means it's going to be iron solid, just straight up iron metal. Fluorine gas. That's one of those diatomic molecules I told you about much earlier. So fluorine always flies together. You need 2 of them for fluorine gas. We've got our yield sign, but it says that it's heated. And that heat isn't going to make any difference to us balancing the equation, but we want to be sure to write it out anyway. And then finally, we've got solid iron 3 fluoride as our product. Iron 3 is Fe3+. Fluoride is F-. Yeah, it's okay. I see your message about your internet. If your internet is choppy, it's all good. The video will be posted on YouTube, so don't worry about it. So for our iron solid, or for our iron 3 fluoride, excuse me, we've got iron 3+, and then fluoride is F-. So we're going to need 3 of those fluoride ions to balance out the 3+ charge from the iron. And of course, it says it's solid, so we put that S there. So were we able to get to at least the equation or some piece of it? How many people were able to piece together what the chemical equation is? Was anybody else able to do it? Y'all are super quiet today. Well, I'm going to just press on. But I really do like to know where you're at. So if you're struggling with something, I need to know. And if you're doing well, that helps me too. What was the question again, Lord Jesus? I was asking how many people were able to at least write a chemical equation from words. So even if you didn't get the answer, were you at least able to do that part? Okay. Now we need to balance this. I make a chart to look at the number of atoms of each element on both sides for the reactants and the products. For the reactants, we've got 1 iron and 2 fluorines. That subscript for the 2 means that you have 2 fluorine atoms. On the product side, we've got 1 iron, but now we have a subscript of 3, which means that we've got 3 fluorine atoms on the product side. Not balanced. We can't just make fluorine appear out of thin air. We're going to find the lowest common denominator for 2 and 3, which is 6. And now we're going to say if I took that 3 and multiplied it by a 2, then I'd get 6 here. So you find the place where your fluorine is, and you put a 2 out in front. That 2, again, is called a coefficient. It's a multiplier. So just like in math, where you have a number out front, you're multiplying everything by 2. With our fluorine on the reactant side, in order to have 6 of them, we need to multiply by 3. So we're going to put a 3 out in front. Now let's take stock of where we are. On the reactant side, we've still got 1 iron, and now we've got 3 times 2, which equal to 6 fluorine atoms. On the product side, we now have 2 iron atoms because of this multiplier here, and 2 times 3 fluorine atoms, which is 6. So the fluorine is balanced, but now we have to deal with the iron. To deal with that, we've got to have our lowest common denominator. And when you have 1 and a number, it's just going to be that number. So we need to add a 2 in front of the iron on the reactant side. Let's do one more final tally. We've got 2 times 1, which is equal to 2 for the iron atoms on the reactant side. We've got 3 times 2 equals 6 for the number of fluorine atoms on the reactant side. We've got 2 times 1, which gives us 2 iron atoms. And 2 times 3, which again gives us 6 for the fluorine atoms. So now we're balanced. The balanced equation, and I'm rewriting it just for clarity's sake. That is our balanced equation. So we had to add a coefficient in front of every compound. You may not need to add a coefficient in front of everything. You may only need to change 1 or 2 things. But balancing chemical equations simply takes practice. So like I said, I will post Chapter 7 practice problems and an answer key. Use it to help you practice the solubility rules, classifying reactions, and balancing equations. So here's your reminders. You've got Chapter 7 Mastering Chemistry assignments due on Sunday. No chapter check-in, just the Mastering Chemistry. You've got Exam 3 coming up, which will be available on Wednesday, and it will remain available until Friday, October 9th at 11:59 p.m. If you're having trouble accessing the exam and you don't let me know until 11 o'clock at night, I'm not going to see it until the next day. So please keep that in mind when you're taking the exam. If you're running into issues, I may not see your message right away. It's likely that I won't see it right away. So make sure you give yourself enough time to take the exam, and if you have any issues or questions, that you give me enough time to get back to you. And we're ending a bit early. Does anyone have any questions related to any of the stuff that we've covered? So exam review. If there's a question on the Exam 3 review that we didn't cover that you'd like to cover, we can do that. Otherwise, we can answer more questions about Chapter 7. So if you're good, you're free to go. Otherwise, you can stay and ask questions and use it as more of a review session. So it's totally up to you. If you're good, go ahead. What's your question?
As far as chapter 7, I kind of struggle with the material in chapter 6, but
Mm-hmm.
is that like basically this chapter is really like about
Yes. Yes. So if you can't name and write chemical formulas, yes, you have to be comfortable with Chapter 6 in order to do Chapter 7. And from here on out, everything builds. So if you're not good with Chapter 7 with balancing equations in particular, then Chapter 8 and 9 will be very difficult for you. So this is the point where, yeah. Go ahead.
when it comes down to like the ions released, like what formula would tell us like would we have like a plus or a negative charge?
Mm-hmm.
That part would be confusing.
Yeah. So you're definitely going to want to review that. And if you can, come to office hours on Wednesday, 2 to 4,
Okay.
and we can do some review there.
All right. Thank you.
You're welcome.